welcome everybody to GeoHug. So before we kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am thrilled that we have Jack Milton joining us today. So Jack is the VP of Geology at Fireweed Metals. And he's driven by discovery and has a passion for testing new ideas and technology in the exploration environment. So he brings more than 15 years of experience in the Canadian North, working on grassroots exploration, resource expansion, and advanced stage development, mostly for zinc, copper, and tungsten projects. So it's going to be awesome because Jack is chatting to us today on the science that drove the exploration to make one of the most significant zinc discoveries globally in recent years at the boundary zone at the MacPass project in Yukon, Canada. So this is going to be an awesome session. I hope you all enjoy it. Please get your questions ready. We'll be opening up the floor at the end. And I will be inviting you all to come on through as a panelist. If you're able to jump off mute at any stage, yeah, definitely please accept and come on through, and we'll get some great discussions at the end. But yes, thank you so much, Jack, for joining. It's awesome having you here today.
Oh, thanks for having me here.
It's awesome. I was very curious before we get stuck into your presentation, what got you into geology to begin with?
Yeah, absolutely. And I knew right away from when I was 16 that geology was my thing, and that's what I wanted to do.
Yeah.
And really for that, I'm thankful for some of the great mentors that I had, which would have been my teacher at the time in high school. I was lucky enough to be in a school in the UK that offered geology in high school, and we did lots of field trips all over the UK. Extensive field work at that time, and that just got me hooked. And I've never looked back, and I've went straight into exploration, and that's really my passion.
That's amazing. And so, yeah, more than 15 years now working in the industry. I'm curious, what have been some of your favorite highlights in your journey so far?
Yeah, absolutely. I think the people who I've worked with is certainly the biggest highlight, and met some fantastic people along the way. I'm also really thankful that I was able to do my PhD in such a spectacular place in the Mackenzie Mountains in the Northwest Territories. I spent a lot of time working in that area, looking at sediment-hosted copper in the Redstone Copper Belt, and that was certainly a highlight. And yeah, another one is what I'm going to be talking about today, which is the discovery of boundary zone.
Yeah, that must have been an incredible experience to be involved in such a big discovery. So yeah, I'm very, very excited to hear about that today. And lastly, I'm very curious what favorite pet rock you've brought along for us today.
Okay, so I got my pet rock right here. Hopefully it's not going to blur out. And there it is. It's a laminated piece of mineralization from the Tom deposit. And Tom is the OG SEDEX. It's where the term SEDEX comes from. It was coined there in the 70s. It's this laminated style of very fine-grained sphalerite, interbedded with barite and mudstone layers. And what I like about it are two things. One, as one geologist once described to me as we were standing on the outcrop at Tom, is it's boring. And what he meant by that, I think, was it's quite innocuous. And if I was an exploration geologist looking for this in the field, you could step over it in the blink of an eye and think it was some kind of laminated mud rock and pay it no attention. But this thing is probably grading 6 or 7% zinc with some lead and some silver.
Wow, that's incredible.
And absolutely. So it just kind of makes you wonder, how many rocks like this have been stepped over out there and are sitting waiting for the next geo who's seen something like this before and stops and recognizes it to make a discovery. So the second thing I like about it is that it's dense. It's very dense. It probably has a density of about 3.7 tons per cubic meter.
Wow.
So, one way you can recognize it is by training yourself to recognize the density of rocks when you pick them up in the field. And it's quite a subtle skill, and it's quite easy with big rocks, but say the rock is only this big, can you tell density difference by picking up that rock? It's quite a subtle skill, but the density that we measured at Tom actually led to a significant resource increase in 2018 when we did our previous resource update. And by measuring bulk density alone, we increased the resource by about 20% because there were just no good bulk density data that had been used to support that resource estimate. So remember, don't be dense, measure bulk density.
I love that. That is brilliant. Well, yeah, thank you so much again for joining us today. If you want to share your presentation now, we can get stuck into it.
Okay, well, thanks very much for the intro. And yeah, let's dive into some of the sort of stories and the science behind the discovery that our team made at the MacPass project in Yukon in Canada in the last few years. And there may be some forward-looking statements that I'll make during this presentation. These should not be unduly relied upon. And here are some detailed notes about our resource. So, what I'm going to talk about is who are Fiery, the company that I work for. We're a junior explorer based in Vancouver, but our projects are in Northwest Territories and mostly in Yukon. And we are focusing on exploration for zinc, but also tungsten. It's a very large tungsten deposit that we own adjacent to this zinc deposit in the Selwyn Basin. So I'll run through a bit about the geology of the Selwyn Basin and what these deposits are like. What are the genetic models that have been proposed for these deposits, and how has that changed over time? And we're going to dive into a bit of the discovery story about boundary and the work that we've done there, and what sort of culminated in this resource estimate that we put out a couple months ago. And then we're going to get stuck into some geology, and I've got lots of rock shots for you, and we'll look at some textures and show a bit of the geology and the mineralizing processes that we infer went on to form boundary zone. And not only what they are, but what's the importance for exploration and why does it matter? And a little bit on what's up next for us. So the MacPass project is on the traditional territories of Indigenous peoples, and we'd like to respectfully acknowledge that our project's located on traditional territories of the Cascadena Nation and the First Nation of Na-Cho-Nyäk-Dun. So where are we? Well, we're in Yukon in Canada, and the MacPass district comprises the MacPass project, which are our zinc assets, and the MacTung project, which is immediately adjacent. And this is the largest high-grade tungsten deposit in the world. We also have a Gainer project. I'm not going to talk about this in this presentation. It's an early stage zinc exploration play in the Northwest Territories. But we're located in the eastern part of the Yukon, very close to the Northwest Territories border. Our project's accessible by this road, and it's within the geological feature known as the Selwyn Basin. So what is the Selwyn Basin? Well, in this sort of pink polygon, the deep pink polygon there is the outline of the Selwyn Basin. And this is an area of perhaps deeper water deposition that is complementary to a carbonate platform that would have existed to the east of this in Northwest Territories. And it's one of the premier districts around the world for large stratiform zinc deposits. So within this basin, we have the past producing Faro mine, which is Faro there. And that is, well, it was at the time when it was operating, the largest open pit zinc mine in the world. And it's not producing anymore, but it was huge zinc deposit. The Howard's Pass deposit is the largest undeveloped zinc deposit worldwide. And we're up here at MacPass, where we've discovered, one of the most significant zinc discoveries in recent years. So a lot of large zinc deposits here. There's some more down in BC, Cardiac Creek, Cirque, and Acai, and they're all located within this Paleozoic Selwyn Basin in stratigraphy that's as old as about Cambrian host rocks through Ordovician Silurian host rocks at Howard's Pass up to MacPass and Devonian host rocks, where we are going to focus this presentation. And overlapping this is a major gold belt, which is an emerging place for exploration with Snowline Gold's Valley discovery, where recently they've defined a resource of over 7 million ounces of gold. There's gold deposits that occur along this tombstone tungsten belt throughout Yukon and the eastern part of Alaska. We also see those intrusions across MacPass too. But what we're going to focus on is the Selwyn Basin and the zinc story there. So focusing in our MacPass, this is what the project looks like at Tom, Jason, and End Zone. That pink polygon is what we started with in 2018. We acquired that in 2016, 2017 from Hud Bay. And we've slowly cobbled together this land package that's now over about 1,000 square kilometers of prime exploration ground in the Selwyn Basin. And Tom and Jason have been known for years, and our discovery is out at Boundary Zone, which is about 15 kilometers away from Jason. And that's where we're going to focus a lot of this talk. But first, quickly, we'll look at sort of this discovery history. So we'll zoom in here at Tom and Jason. Now, Tom was found in the 1950s by prospecting. That road that runs right down the middle of our property is the Canal Road that was put in during World War II for an oil pipeline, and it opened up the area for prospecting. And Tom was found by traditional prospecting. They went up the creek that was bright red, iron-stained creek, and found Tom sticking out the ground as an outcrop. Now, Jason, who's only 5 kilometers away, was not found for another 20 years, and that was done by soil sampling and gravity. And End Zone was found another 5 or so years after that. And then Boundary sits out here, sort of down this trend. So what attracted us to Boundary in the first place was what we saw there was the potential for a very large hydrothermal system. So with more than 2 kilometers of strike length that had sort of sniffs of zinc mineralization and siderite alteration throughout there. And Cominco had drilled this in the 80s, and they got some very long intersections over 200 meters of about 2, maybe 3% zinc, but grades that weren't really going to cut it on average there for this part of the world. And we also saw evidence for a lot of extension. We saw these volcanic rocks, these volcaniclastics, these subaqueous, mafic, explosive eruptions. We see diamictites, these slump breccias that are sloughing off of these sedimentary faults. Extensive siderite alteration. There's iron carbonate that comes along with some of the sphalerite. And right next to one of the major structures in the area, the Hess Fault. However, the host rocks at Boundary were the wrong host rocks for this SEDEX model, this model that had been proposed for the Selwyn Basin in the 1980s and late 1970s. And we were just in the wrong part of the stratigraphy. And we'll come back to this, but we persisted with the idea that perhaps we could look elsewhere in the system and make a discovery. So these cartoons kind of summarize these evolving genetic models in the Selwyn Basin. So what kind of deposits are these? Well, these are stratiform, sediment-hosted zinc-lead-silver deposits. And we see this at Tom, Jason, End Zone, and Boundary Zone. Some people call them plastic-dominated or CD deposits, but we no longer refer to them as SEDEX deposits. We don't use that term because it's genetic, and it implies that the mineralizing process was associated with the exhalation of fluids into reducing seawater and the formation of sulfides within that reduced seawater. And the more recent work and research that's been done on these systems has shown that they form in the subsurface by replacement. So even though these fluids would have exhaled at some point, that's not the mechanism by which these sulfides are forming, and they're forming by replacement in the subsurface. So this old classic model, this ZX model, has been sort of superseded by this new model for mineralization. But in talking to Rob Kahn, who proposed this model in the 70s, it's interesting talking to him that he noted that they also recognized inhalative deposits at the time. And these were deposits that showed evidence of subsurface replacement, and that some of these textures were recognized at the time. So what does this new model look like? Well, it is a two-step model, and the first step is the formation of stratiform barite accumulations in the subsurface. And this would happen in very shallow burial, just above the sulfate methane transition zone. So you have an upwards flux of barium and methane and a downward flux of sulfate coming from seawater. And within this, you can form these diagenetic barite lenses in the subsurface. And this is a sort of form of host rock preparation, if you like, for subsequent zinc mineralization. You're forming a source of sulfur, which will then get reduced during mineralization. So that second stage is these zinc and lead-rich fluids coming up the fault, interacting with that barite, reducing it into sulfide, and forming sulfides by replacement of these barite layers in the subsurface. And you see these accumulations of barite throughout Selwyn Basin, both on the platform and down in Selwyn Basin, and you see them in areas where there's no zinc, where they are just diagenetic barite accumulations. And these are areas that did not form zinc deposits. They weren't plumbed into a system, into a large structure that had mineralizing fluids come up. And this is all sort of evidence towards this model of this two-step process. So we followed this model in our exploration for zinc at MacPass. So we'll dive into a little bit to the geology of the Tom deposit, and we've just put a resource out. This resource covers Tom, Jason, End Zone, and Boundary Zone. It's a resource update for Tom and Jason, and it's the inaugural resource for Boundary Zone and End Zone. But at Tom, we domained the resource into very well geologically defined domains of massive sulfide, which tends to occur at the base of this tabular zone. You can see it's dipping 60, 70 degrees here. And the mineralized zone is comprised of the massive sulfide facies, the pink facies, where the sphalerite turns a little bit pink, the gray facies, where the sphalerite is a bit more gray color, and the black facies, where you get more mudstone and less barite. And so these are the sort of classic textures that you see, this laminated, very fine-grained sphalerite mineralization, and the form of the deposits is in generally a single stratiform zone. It's parallel with stratigraphy and stratobound into a particular part of the stratigraphy. And so very well-defined contacts and sharply defined tabular zone. So we set out doing some exploration. We had acquired the property in late 2018. We drilled a couple of holes at Boundary Zone in 2019 to support, it was actually an ore sorting study. And we got some pretty good grades there, higher than historic grades. It was encouraging. And we put all the geology together in 3D. We modeled it, and we set out in 2020. And I remember it was the COVID year. Not a good year for anyone that year, including our stock price and ability to raise capital. So myself and this geologist on the left here, Quinton Willems, we had packed our bags full. They weighed about 100 pounds each, and we couldn't afford a helicopter because we couldn't raise any money. And we were going to hike 20 kilometers through the bush to go prospecting at Boundary Zone. And, we were hefting these packs onto our backs. And the satellite phone rang just as we're about to leave, and it was the CEO saying, "Don't go. I'm going to raise some money. We're going to do a drill program." And we did. And that was late in the season in 2020. And we organized a ground gravity program, a boundary zone, followed up by a drill program. And these are some shots from that program. And what were we looking for? What had we set out to achieve in that program? Well, we looked to Red Dog as an analog for the geology of what we were seeing. And the holes that we had drilled in 2019 and the historic core that we'd seen a lot of this vein type material. And it's very different to that fine-grained laminated mineralization that we see at Tom and Jason. So we thought, what could this represent? Well, the closest analog we found was Red Dog, and this is from a paper describing the geology of Red Dog, and that green material in the section is their vein ore, which looks like these pictures on the right. And the initial discovery at Red Dog was actually made in this vein ore material. And it wasn't for a number of years of exploration until they drilled it out that they figured out that the highest grades are actually associated with these replaced barite layers in the massive sulfides. And so we thought, okay, well, maybe there's a similar thing going on at Boundary Zone where we've discovered some of this vein type ore or mineralization. And now let's look and see if we can find some of these barite layers that may be replaced by massive sulfide. And a couple of years ago, I had the pleasure of going to Red Dog and standing in some of the open pits there and picking up material which you could hold in one hand and hold a lump of boundary zone in the other in this vein material, and you would not be able to tell the two apart whatsoever. Very, very similar textures in what we saw there. And so this drill program, you won't forget this, when a driller called across the radio and said, you know, Jack, you better come and take a look at this. And you know when the driller's saying that you've hit something good. But the weather was coming in that day. It was kind of cloudy and foggy at Boundary, and we move all the core back and forth with the helicopter to the camp, which is about 25 kilometers away. And the weather was too bad to transport the core that evening, so I had to try and sleep all night, which I didn't sleep a wink, and get up the next morning like an excited, you know, kid on Christmas morning to go and open their presents and see what we hit on these core boxes. And this is a photo of us, you know, taking the lids off those boxes and seeing just row after row of massive sulfide. So we hit 26 meters of massive sulfide on hole 4 in 2020. And that was when we knew that, you know, we'd hit part of the system and, you know, high fives were had, and it was a very exciting moment. And that intersection graded about just over 75 meters of 4% zinc, including the massive sulfide section of 24 meters of about 6.5% zinc, 0.75% lead, and 47 grams of silver. And this stuff is truly massive sulfide. It was 100% sulfide, more or less. The bulk density you can see there, the average is over 4 tons per cubic meter. And you know, some of the stories about helicopters not being able to take off because they're carrying, you know, so the core's too heavy, there's too much metal on it. It's true, it happened several times to us where we couldn't move the core. We had to take a few boxes off to move the core back to camp because it was just full of massive sulfide. So remember, don't be dense, measure bulk density. So this is what the discovery story looked like in map form. So these are the holes that Kaminko had drilled in the 80s. And what you're seeing behind there is the gravity map. Kaminko didn't have that. So this is something that we did in 2020 with that gravity survey. And we noticed on the western side of Boundary, there was a large part of this gravity high that had not been drilled. And so this geophysical anomaly attracted us to this area. But we'd also drilled the holes in 2019, right in the middle of that cluster of drill holes there. And we'd noticed near the end of one of these drill holes of some barite, some of these barite snowflakes that we see, these indications that you're in an enriched part of the stratigraphy. And we projected this area, and in 3D, this layer projected out west to where this untested gravity high was. In combination with that, we had some historic soil data, and we were getting up to a percent barium in soil. And so we were very excited to go and drill this. And this is, what we put the first year of drilling. We did this and we made the discovery with one of those holes on the west there. It's where we hit that 26 meters of massive sulfide. And since then, we've drilled quite a few more holes into boundary. So this map shows all the holes that we drilled up to the end of last year. So this doesn't show any 2024 drilling. We've done a whole season of exploration since then that we're putting results out right now. And we've defined a very significant deposit using all this drilling data. We put together the model. And this is a series of long sections that I'll walk us through here, looking at this stratiform layer of massive sulfide that we found at boundary. So we're looking north, this is a long section. The green is this vein style mineralization, and the pink is this laminated stratiform mineralization, and the purple. And back in 2022, this was sort of the state of play. We drilled our best hole ever down at Boundary West that was 103 meters of 14% zinc. This was on one side, and then on the other side here, we drilled a hole at Boundary Main that was 4.5% zinc over 298 meters, including a very high grade 24.5% zinc interval of 9.6 meters in the stratiform mineralization. And we had all the indications geologically that we were getting hotter towards this part of the system. We were getting increased zinc grades, we were getting increased lead to zinc ratios, more lead, more silver, more copper, not economically interesting amounts of copper, but geochemically anomalous amounts of copper were increasing. It's showing us that we were hotter, we were increasing silicification towards this area, and more diamictites, more of these slump breccias. And there was a potential feeder fault that bisected this area that we thought was sedimentary and therefore could be a feeder fault. So we set up for the 2023 season, and this is another long section showing the same area with that untested potential feeder zone. And we drilled some of our best holes ever, which then eclipsed those previous holes. So in hole 7 from 2023, hit those two separate intersections of fantastic grades and thicknesses. And hole 28 eclipsed that with 143.9 meters at 14.5% zinc, over 1% lead, and a couple ounces of silver over a true width of 50 meters. And by the end of that season, we defined a long section with contoured true thicknesses on it like this, where we just kept on getting higher grade and thicker true thicknesses within this massive sulfide zone to the core of the system, where it was over 40 meters, it was 40 to 50 meters thick. And you would get that table of highlights there. We were seeing zinc grades of sort of between 11 and 19%, lead 1 to 2%, and 60 to 115 grams of silver with very high bulk densities. And so this is one of these laminated massive sulfide zones that we see at boundary. It's tabular, it's steeply dipping, just like Tom and Jason. But importantly at boundary, we see this zone, which is in the mid-Devonian host rocks. We see another zone right next to that called the upper zone. And then up here in the stratigraphy, we see the full lake zone, which is the same level as the Tom and Jason deposits. And we also see mineralization down lower in the stratigraphy in what we term the Howard's Pass interval. We call it that because it's hosted in Ordovician to Silurian host rocks that are the same age as the host rocks to the giant Howard's Pass deposit. And we know those ages very well. They're very well constrained because we drilled and recovered graptolites from the core around these intervals, and we had them identified by a graptolite expert like Milton. And it absolutely nailed the age of the stratigraphy to the same age as the Howard's Pass deposit. So we have multiple layers in the stratigraphy, Ordovician Silurian, Mid-Devonian, and Late Devonian, that all have these tabular, laminated, stratiform zones of zinc mineralization. And so that's a little bit unique for boundary, unlike Tom and Jason, which is just at one layer in the stratigraphy. And we defined a resource that sits like this. So we have about 56 million tons of indicated at 7.3% zinc equivalent, in addition to 48.5 million tons of inferred at 7.5% zinc equivalent. And in terms of our global rankings, this is where it puts us amongst some of the best and largest undeveloped zinc assets that are not held by majors. And so what do these rocks look like? Let's dive into some geology at boundary. And we see this feeder zone facies. And by this feeder zone, this term has superseded the term vent facies that would have been used in the SEDEX model. But if these fluids are not venting at this point into seawater, then we shouldn't call them vent facies. We should call them the feeder zone facies, because you're feeding this barite layer at this point. And that's what it looks like. So we have massive sulfide on the left. This would be closest to the feeder. It can be up to 100% sulfide. Sometimes you get remnant mudstone patches within that. Sometimes it's all pyrite, and sometimes there's a lot of sphalerite and bits of galena, as well as the pyrite. And then this grades outwards and laterally into the pink facies. So it's laminated, very fine-grained pink sphalerite, and then grades outwards again into the black facies where the sphalerite becomes gray and is interbedded with mudstone and pyrite laminae. But importantly, there's a second style of mineralization that you can also see on these photos, and that is the cross-cutting layers of very coarse pyrite and sphalerite. And these are these veins, that is this ore stage 2 or mineralization stage 2 that we'll come back to. But importantly, these fine-grained laminated zones appear very similar to those textures that we showed from Tom and the different domains that we defined in our resource there. And within these stratiform layers, we commonly see these barite textures. So we see these needles or laths of barite. Sometimes they're arranged in these radiating splays of barite needles that we call snowflakes, that have then been pseudomorphed and replaced by sphalerite, by pyrite, by galena, sometimes by silica. And it's showing that barite is being replaced in the subsurface. And so this is the vein style mineralization that we come back to. And it's not just veins, but we also see hydrothermal breccias developed. And we see flooding of coarse clastic rocks, conglomerates, diamictites, volcanoclastics. We see flooding of those with sphalerite. And it's always this coarse red-colored sphalerite, and it's often accompanied by siderite and pyrite. But we see that same mineral assemblage in either simple veins, like some of these, or much wider, more complex banded veins, or within the cements of these hydrothermal breccias. And this is what boundary zone looks like in terms of the geology model that we built up. We built up a fault model, we built up a lithological model based on sequence stratigraphic principles. So we use marker layers within the stratigraphy that we identified geologically, lithologically, and chemically, and we built up consistent lithological units between these markers to define the stratigraphic model. And we found that these stratiform laminated domains, that we've highlighted 2 of those on this section, form these tabular zones, but also that the grade continuity in the vein mineralization follows that same kind of stratiform trend. And so we modeled all of that. We put a halo around it, that pink bucket, which caught all of the mineralization outside of those well-defined domains, to bring that into a resource that we constrained with a pit shell, just so you can see on this section. And the vein domains we defined as min 1 to min 13, and these comprise a significant amount of the volume of mineralized material at boundary zone. So here on that pie chart, you can see the distribution of tonnage between the massive sulfide and laminated mineralization in pink, which is just less than 1/3 of the tonnage at boundary. That's about 15 million tons, versus the vein and halo mineralization, which makes up for over 2/3 of the material, a boundary zone. So they're quite significant a boundary in terms of their overall contribution to tonnage and metal content. And this is completely different to Tom and Jason, these classic Selwyn Basin stratiform deposits. We don't see this style of mineralization, this second phase, this overprint with veins and breccias at Tom and Jason. This is unique to boundary zone. So what do these veins represent? Well, in this image of a hydrothermal breccia here, you can see the clasts are very, they're not very well rounded. They're nice and pointy and sharp. And on that inset where we've zoomed in, and the pink arrow is pointing at a stylolite, and these are mud rocks. So stylolites can commonly form in siliciclastic rocks. They're not unique to carbonate rocks, and they can quite commonly form, particularly in very silica-rich mud rocks. And what's the significance of this? Well, this gives us a hint about the timing of mineralization of this vein and breccia style mineralization. The stylolites that we see are not burial compaction related stylolites. These form at a high angle to bedding. And so these stylolites represent compression and compaction where this rock is dissolving under pressure, likely during a significant orogenic event. And these stylolites have formed prior to these breccias because they are present within the clasts, and the stylolites do not extend outside of those clasts and into other clasts. So this tells us that this phase of mineralization would have occurred syn to post a significant orogenic event. And in this area, that orogenic event would be the formation of the Cordillera, the Cordilleran orogeny, which would be in the Cretaceous. So this could be up to 200 million years from when these host rocks were deposited, that we see a very significant volume of zinc either coming into the system or being remobilized. Here's another shot of a hydrothermal breccia. Now, this time we've got 3 different pink arrows on here, and they're each pointing at the edge of some of these clasts. And those edges are defined by this castellated texture with an insoluble black thick residue at that clast boundary. And that's telling us that this is a stylolite and that this breccia has developed along the stylolite and has fractured the rock using that stylolite as a pre-existing structural weakness that's formed a precursor to these breccias. Here's another example, and this time we can see that breccia developed between 2 stylolites, and that we have an explosive breccia development forming these clasts, and the sphalerite, that sp2, that sort of red color sphalerite developing as the cement of these breccias. So there's a significant structural story related to these stylolites. So what is boundary zone? Well, this is a little sort of teaser from a paper that will be published shortly in Economic Geology by Haruna Grima, whose PhD student has been working on boundary zone for the last few years. And this sort of is a genetic model that summarizes what we think is going on for boundary. Well, at the top section of that cartoon, in ore stage 1, or mineralization stage 1, we have the red sphalerite occupying several different layers in the stratigraphy. Down in the Dewar Lake Formation, that's the Ordovician Silurian, the Howard's Pass age rocks. Up in the Niddary Lake member, this is the mid-Devonian rocks. There's actually 2 different intervals within there. And then up in the Fuller Lake at the top there, that is the same stratigraphic interval as the Tom Jason deposits. So we have stratiform mineralization within rocks of different ages spanning the latest Ordovician through to late Devonian, which is a significant time interval in itself. Did these stratiform mineralization occur all at once in one event? Were they 3 separate pulses at different times? We don't know exactly, but we suspect that they formed in one event because the paragenesis and the mineral assemblages that we see in each of those layers is very similar, and we infer that they may have formed as one event, as replacement in the subsurface. And this is why, going back to the start of the presentation, that it was really important for us to not just look for that Tom-Jason layer in the stratigraphy, which would have been that upper Fuller Lake member, but to open up the search space and look in a much wider stratigraphic interval for anywhere where we had reactive host rocks, so barite, and barite that could get replaced by these mineralizing fluids. And so this is this ore stage 1 at boundary zone. And then ore stage 2 came in potentially significantly later, could be 200 million years or more. And with that, we see development of banded veins, of breccias, possibly pre to post folding of those rocks during that deformation event. Does this form due to tapping the same source of zinc at depth and bringing in more zinc into the system? Or are we remobilizing that zinc somehow? Perhaps these stylites that form dissolved significant portions of that stratiform mineralization by pressure solution, forming a hyper-enriched zinc-rich fluid, which then jacked open these stylites and precipitated pure sphalerite in the cement of these breccias. Possibly. So what does this mean for exploration? So on the left here, we have all these processes that we've talked about. And on the right, the exploration criteria that we've developed from these processes. So first one, replacement with barite. Replacing the barite, possibly carbonate too, but that's kind of another story. But let's just use barite as the example, is that basically you can enlarge that search space and look anywhere in the basin, not just at the Tom-Jason layer, but any prospective parts of the basin that have that right chemical host rock. Now, we've found that at boundary at 3 different layers, one of those being the Tom interval, but we know there's at least 2 other layers in the stratigraphy in the Selwyn Basin where there's no known zinc systems. Now, to me, that's a great place to go out and look for significant zinc deposits. Well, what else do you look for? A long-lived system. And at boundary, we see textures, overprinting textures that clearly indicate there were at least 2 pulses of mineralizing fluids that may have utilized the same fluid flow architecture and plumbing system. And this may favor the formation of larger systems. So what do you look for in exploration? Well, multiple cross-cutting phases of mineralization in close spatial proximity. Now, this one I think is a nice to have. It's not necessarily a must have. Tom and Jason, you don't see this, but Tom is a larger deposit and has more metal than boundary zone. But I think the presence of it could be favorable for exploration. Sin sedimentary faulting is another thing that we infer to be exploited by these fluids, and these long-lived large-scale faults where they intersect a reactive host rock seem to be important in this process. And what evidence do you use to look for sin sedimentary faults? Well, this is quite difficult to actually pin down in the field and say this is definitely a sin sedimentary fault, but you can infer this using evidence from diamic-type debris flows. For example, at the Jason deposit, these have been mapped out in 3D, and these debris flows can be seen to be thinning off of the fault scarp, which has been drilled through and is mineralized and is clearly sin sedimentary. You can also look for lateral changes in the stratigraphy, big picture changes, missing units, changes in the lithofasces of certain units across structures can infer that they were there early in the basin. You can also look for unusual fold patterns, like we see at Tom, and perhaps strain has been partitioned differently around these faults during deformation. At boundary, you also see these proximal volcaniclastic rocks, these fluidal class breccias in these mafic explosive subaqueous volcaniclastic rocks and fault reactivation. But I think one really important point that can perhaps be applied to not just zinc, but any kind of system is the natural variability that we see amongst these systems. So we see that each mineralized system is unique, and that these large deposits can form from a variety of processes. Well, you know, that's great, but how do you use that in exploration to narrow down your focus? And I think here is where perhaps it's not your focus being narrowed down, but keeping an open mind and not being extremely model driven, not completely throw out the models. They're useful for certain things, but not be so restricted to them that we ignore good data or a good sample that just doesn't fit the model. And so using a data-driven approach and keeping an open mind, I think, is key to sort of combat this natural variability that we see in these systems. And, you know, we've seen Tom, we've seen Jason, we've seen Boundary, but our next zinc discovery may look completely different. And I think it's important to keep that in mind as we explore for them. And so, you know, we see a lot of potential across this district for more discoveries. And we've defined this prospective corridor that has the right structures and the right stratigraphy. We think these feeder faults and sedimentary faults occur approximately on this periodicity of 5 to 10 kilometers apart. And we had a very large exploration program this year. We spent $5 million, not including any of the drilling that we did, just on regional exploration, gathering new gravity data sets, soil sampling, prospecting, mapping, and ground truthing some of these things in an effort to find another deposit along the trend. And so what are we left with here at MacPass? Well, this is really a critical minerals district. With the deposits that we have here, zinc being a critical mineral, tungsten being another critical mineral, and we have the world's largest high-grade tungsten deposit just next door, only 10 kilometers from the Tom deposit is MacTung, where we have this world's largest high-grade tungsten deposit. But we also have two other elements. We've not mentioned gallium and germanium. And in the resource that we put out, we included these as byproducts and reported them alongside the mineral resource. Now, we did not attribute any value to these in our resource. They do not contribute to our zinc equivalent calculation. They do not contribute to our NSR calculation. And this is because there is no precedent for these metals being payable in a zinc concentrate. So essentially, these metals have no economic value to an explorer or a miner. They are extracted by smelters, zinc smelters that have germanium or gallium circuits, and they are sold by those smelters who make money off them. And you may anticipate perhaps a reduced treatment charge for those zinc cons, but we don't attribute any direct value to gallium or germanium. However, this is the largest known accumulation of these metals on Earth. So it's a very significant amount of gallium and germanium that we have, and we see value on getting on the radar of government initiatives that support critical minerals projects. And here at MacPass, we have, you know, the world's largest tungsten deposit, one of the world's largest zinc deposits, and the largest concentration of gallium and germanium that's known on Earth. And we think that this makes this a real critical minerals district. And so what's up next for us? We'll be putting our drill results from this year out throughout Q4 this year. We've had this huge regional program, and we're going to optimize our 2025 exploration program to set out and try and find another one of these deposits, but continue to explore and advance and discover mineral resources at our existing projects and continue our engineering studies to advance those along. So it's going to be an exciting next year, I think, for us at Fireweed. So watch this space, and I'd just like to thank everyone for listening to my presentation.
This has been fantastic. Thank you so much for chatting to us all today. That was awesome to hear about. So thank you.